Welcome everyone at part 10 or session 10. In this part, we'll talk about a very important neural network architecture, which is called the convolutional neural network. In the similarity major session, we talked about the convolution and how it works on basically detecting local features on signals or on images. So this is the idea of convolutional neural network, but today we'll go more into details about the functionality and about the building bricks of convolutional neural network, which is also called CNN as well. So, as I said, we have seen in the similarity measure part, the convolution in convolution, we have the template which is red, and this template is scanned or passed along a signal which is here in the blue, and where we have a match, basically, so it's also called template matching, where we have a match between the feature or the template and the signal, we would get a high intensity value in the feature maps. And this do the dot product, because we have said that convolution is actually a dot product what is scanned over the signal. So convolution is done by scanning the template over the signal and applying local dot product and storing the result in transferred output signal. We will basically learn now in more detail what the meaning of that. Let's assume we have now not a signal, we have only a part of that signal, which is here either sample 1 or sample 2. We have two features space, x1 and x2, where x1 represents the first pixel or the first value of that signal, x2 here represents the second pixel of that basically signal. If you are talking about 1D image, then this is a pixel. If you're talking about a real signal, then this is basically the index here, what is the same. Now, x1 is x2 is a scale between -1 and 1, and this is why also scaling or normalization is important for dot product. Here, for example, we have -1 and 1, and -1 and 1. This is our range of x1 and x2, the possible values. 1 means total whites, which is an image basically in image processing or in image themselves. It has a value of 255 usually. So 255 is the highest intensity value, which is white, and 0 there is black. But when we scale it now, it would be 1 is the white and -1 is dark or black, actually completely black, and 0 would be here in this case gray, so in between white and black. So our template has this basically values -1 and 1. So the first pixel has -1 and the second pixel has 1, which represents usually an edge in this image. If we see such a template or such a feature, this represents an edge in the image where we go from low to high. Edge is always when there is a change in the intensity values, where there is high, sharp, basically change in the intensity value. This is where we have an edge. As I said before, let's look at this part here, where we have here a kind of, for example, close to white. Then when it goes to red, directly there is here a sharp change from white to red. And this is basically, we have an edge here, and also we have edge here. These are basically when we have sharp changes. So this is our template, and we have here two samples of possible signal values. The first one, sample 1, has a value of -0.7, which means it's actually dark, but not as dark as black, and 0.5, which also means it's also quite bright, but not bright as the white one here. And here we have sample 2, which is equal 1, which is basically white. Now we want to compare these two. Actually, we want to do similarity using dot product between the template and sample 1 and the template and sample 2. If we plot them here into these 2D vectors, vector space, our template or feature is this one because it has a value of x1 -1 and x2 equal to 1. This is the first sample, x1 here, x basically big 1 here. which equal to minus 0.7 and 0.5, and here x2, which is 1, 1. So dot product, as I said, is similar to cosine product. Cosine similarity, because basically the cosine similarity is the dot product divided by the multiplication of the magnitudes. So if we ignore the magnitudes, dot product and basically cosine similarity, they are the same. And especially if we are talking about this kind of space between minus 1 and 1, then dot product and cosine similarity, they are very similar. And when we talk about cosine similarity, as I said, the smaller the angle between two vectors, the more similar they are. For example, here we have this small angle between w and x1. That means they are way more similar than the angle between this one and this one, which is here about 90 degrees, which is basically it's the one because the cosine similarity equal to 0. And we can see, for example, when it comes to dot product, for example, this is actually just, this is x2, where we multiply it with the template. So the first one is the template, the second one is the feature, which is either this one, x1 or x2. For this one, it has value 1.2, which is way higher than the second one, which has a value 0. And as we see, basically, here it has no similarity at all. Here it has high similarity. And this is basically the idea of dot product as similarity measure. And this is how it's used in the image processing. This is how it's used in the neural network, as we have talked about in the previous lectures. But also, if we look here at these two features, just by looking at them, we know that these two are more similar than these two, because here we have dark white and here we have gray, also basically close to white. So basically, this kind, as I said, of changes, sharp change between two colors, this is what we are looking at. And this is how we can detect, for example, such edges within signals. So this is using only features, but let's talk about now signal, where we need to apply now a convolution. So we have now this signal, which is basically x1, x2, x until here the last one, for example. So this is a set of pixels, and they have different values. They can have random values, but what we are looking at, basically, we have this reference template, the feature, and we want to find where in this signal we can find similar features to that. So as I said, dot product is basically scanning of, the convolution is scanning of that template along the signal and doing dot product at each position, then storing the value in the output signal. So at the beginning, we have this output signal, which has the same size now. It will be reduced, but let's say we have same size as the input signal. And we are at the position 1. We do the dot product between these two. We get the value of -2. And we store the value at this position in the output signal. So whenever we are here, we store it at the first pixel. This you choose it. For example, you can store it at the second pixel. This is not, it doesn't really matter. We will talk about later the pooling, which makes the basically the local invariance important, like here. And so, for example, now this is our first product, and we get -2. Now we move to the next position. This is a convolution, so scanning over the input signal. There we get 0. Now these two are a bit more similar than this one and this two, which is basically here it's completely the opposite. But for example, we continue at this position, it's also more similar. So you start to see here basically an increase in this similarity. And here we have our peak in the similarity, because this is basically 1.2, where we have this edge, which is really similar to what we see here. Then we continue, 0.5. Now it starts to decrease again, 0, 0, and 0. So what we see now is basically we did the convolution. We moved this signal over the input signal or the target signal here, or 1D image, for example. and we get the feature map. This is called the feature map because it's basically the result of convolution of that feature over the input signal. And we see here kind of a peak or highlight. And this peak basically tell us that at this position, I found a feature, or I found basically two pixels that are very similar to my target feature here. For example, if we do this kind of it's called edge detection template, and this is our input image, and if we do convolution of that two-dimensional pixel, we'll see later how we do that over this input image, we get the feature map where everywhere basically most of the pixels they are dark, but we have some bright pixels. These basically bright pixels represent edges, and these edges basically they are similar to the structure or the values of that template. Like for example, here we see that a bright pixel here. So this is about 1D convolution. Now 2D convolution is exactly the same, but it's done on basically matrices. Because an image is not 1D, it's 2D or 3D when we consider the colors, RGB colors, for example. But when it comes to 2D now, for example, we have the input signal or the reference signal as a matrix. So here, for example, the columns and the rows, and this is basically usually YX. And here, for example, we have the pixel values inside. These pixel values usually in images, as I said, between 0 and 255. What we usually have to do always to scale them or basically normalize them to the range between -1 and 1. But here it's between 0 and 1, it's not a problem. And we have this filter. It's an example of filter, whatever this filter represents. Just consider that is -1 to 4, just a random filter. How we do that, it's exactly like we did with 1D. What we are doing actually, now we start with the first possible position of that filter along this image. For example, this filter cannot now start, for example, if this is the origin of the filter, we cannot start from here because here we don't have pixels. So we need to start with this first position because it's the first position that the filter fits within the image. And then we do dot product, and the dot product here basically we multiply each pixel in the filter with the corresponding pixel in the image, in that local image basically feature. So here, for example, what we are doing, we are multiplying -1 with 1, +2 with 0, plus -2 with 0, +4 with 1. This is our dot product now. And here we have a bias, because in the neural network, we always have the linear model, which consists of first multiplying the weights with the input plus bias. And this bias here equal to 1. It could be equal to 0 if we don't want to bias. But for example, if we do that multiplication plus the bias, we get 4. So we set now the value of 4 here at the output at the feature map. Now we can see that the feature map has 3 by 3 now size, not here 4 by 4. We will see later what is the effect of the filter size and basically the stride or the step size, and if we have padding or not to the feature map. But now let's say that at this position we have now the value of 4. Then the second step, we move that filter one step to the right side. We apply convolution again by multiplying -1 with 0, 2 0, 4 0, -2 with 1, and sum them, plus the bias, it will be equal to -1. Here we continue with the third position as well, and we get 7. Now in the next part it will be here, so it will be to move basically to that position, the origin I mean, from here to here. Then we would multiply 1 with -1, 0 with 2, 1 with 4, and 1 with -2, sum them. So if we can repeat that, for example, to the whole image, we will get this feature map. Now if I look at this feature map, basically I can see here at 7, and 7 we have the highest, let's say, matching between the filter and the input image. So convolutional neural network has a convolutional layer. And what is a convolutional layer? is basically has two steps. The first one is the convolution that we have seen here, where we have the input image, we have a filter. The convolution layer could have now multiple filters. The filters here are like neurons in the feed-forward neural network. For example, feed-forward neural network can have also multiple neurons. And here is the same, the convolution, it would have multiple filters. And these filters, all of them would process the input image and create a feature map. So this basically you can consider it like a single neuron in the feed-forward neural network, but this is a convolutional neuron. And here we start with the convolution. We add the bias. If there's a bias, we get the feature map. Then also we apply nonlinearities, which means we apply an activation function. For example, if you are using ReLU, ReLU would put all the negative values to 0 and would keep the rest. For example, if I have ReLU here, this one -1 would be equal to 0, and the rest would be as they are. So this is the convolutional neuron. And if I have multiple neurons like this, from this one, it's convolution layer. So what is then convolutional neural network? It is, of course, a combination or basically a sequence of convolutional layers. And if we look here basically at the convolutional neural network architecture, or the general convolutional neural network architecture, we usually have an input image. Then you would see convolutional layer, which is convolution plus ReLU. Okay, so we have convolution first, then ReLU or any activation function. But again, ReLU now is the most common one. Then we have a set of, for example, in the convolution layer, we have a set of features, a set of templates, which means a set of neurons, as I said, like in the feed-forward. Let's say we have 3 neurons only. That means we will get at the end the 3 feature maps. Each feature map represents specific feature. For example, one would represent this one, the other would represent another feature map, and so on. Now, the next part we see is something called pooling. So this is, I put here question mark, what is pooling? I will talk about that later. But the idea in convolution network, we have convolution, then pooling, then convolution, then pooling. And these two, basically, the convolution pooling represent one, you can consider one layer because it's one block. And here, for example, is the deep neural network. So we have many or multiple, we could have multiple convolution pooling, and so on. Then we have what is called fully connected. We also talked about, which is actually here the normal feed-forward network, which we need to have in order to do softmax at the end, in order to do classification, for example, between dog, cat, bot, and bird, and so on. You could also sometimes see this kind of representation, which is the same as this one. Here we have 3D because now each filter, as I said, would create a feature map, which is an image, some kind of image with highlight within. And here basically all features map because here depends how many features we have. If we have, for example, 100 features, then we have here 100 feature maps. And of course, this is the size of the image for the other 2 dimensions. Now the pooling layer, which is we talked about here. What is the role of this pooling layer? So the first functionality, or the main functionality, is downsampling layer, which means we need to downsample the feature map. Downsample means we need to reduce the size of the feature map. So reduce the size, for example, has at the beginning one objective. We need to reduce the size of the images because the big images, if we have, let's say, 1000 by 1000, then we are doing really a lot of convolution terms or operations. That means, of course, we need to here large memory, we need the large computational power, and so on. So the idea of convolution is basically to reduce the size of images as we go deeper and deeper, because with that, we are actually, first of all, making the computational basically speed faster, and also we are reducing the complexity of the network. And also because at the beginning of the image, let's say if we are trying to detect the bot, the most of the pixels here are unimportant, like the background, and what is important actually the pixels of that bot itself. And this is the idea of also downsampling, because at the beginning we have a lot of unimportant pixels, we have a lot of redundancy, and basically what we are doing along this deep network, we are trying to remove all the noise, all the unimportant features, and keep the important features at the end for the software to do this decision. So it scales down the amount of information just by the sampling, which is generated by the convolutional layer for each feature, and maintains the most essential information. So pooling layer also makes the neural network less sensitive to the location of the feature in the input space. So if the input, if the feature is, for example, is in different positions of the input space, the pooling layer makes it easier or makes the network less sensitive to that, which is called local transition invariance. So what is a pooling layer? It's basically downsampling. There are different operations to do that, the downsampling. They are either max downsampling or max pooling, it's called, or average pooling, for example. These are the two most famous. Max is actually what is very common. Convolutional layer, we have seen it before. So we generated basically the feature map out of the convolutional layer. And now we have a max pooling here. So the max pooling, first of all, or the pooling layer has also kind of a template here, or kernel, which is its size could be also one of the hyperparameter. And here we have, for example, template 2 by 2. What we do here, we also move that template along the feature map like we did with the convolution, but the operation here is different. At each position, we look at all the pixels within that kernel, and we pick up the highest value, the maximum value of that position. For example, we have 4, 0 to 7. We pick up the 7, and we put it at the output signal. You can see we reduce the size first of all, because here we had 3 by 3. We end up with 2 by 2. And this basically we are removing the unimportant now values, because here what we got as a conclusion that we have really 7, which means that this feature actually is detected in the input signal because we have this value, regardless where it is now. We basically by downsampling, we put it like, for example, that we have highlight that this feature is detected because it is here or here, or if 7 was here, actually it would be the same, or here it would be the same. This is what the idea of the local transition invariance, okay? And the idea of basically downsampling also reducing the size, because here we had 3 by 3 and we got now 2 by 2. So this is a pooling layer. Let's say we have here another example. We have basically 4 by 4 feature map. And again, we have 2 by 2 max pooling. Then we start from here. We pick up the maximum value, which is 6. Then we move by stride of 2. I'll talk about stride later, which is actually step size. And then we pick 8. Then we move here down, and we pick basically 3. Then we move here and pick 4, and this would be the output of the pooling layer. The same thing when it comes to images, or actually this is also an image, but let's say when we look at the pixels here, this is basically 24 by 24, and when we downsample to 112 and 112, you can see that it's not that different. We just reduce the size, and now we have less number of features, less number of neurons, or actually pixels to deal with, which actually better also for the computational power. So now we learned about the convolution, pooling, and now what is next is it fully connected. So always neural network, in order to make the final decision, we need to flatten, which means we need to vectorize our vectors, because a softmax that we have seen before, which is a part of feed-forward neural network, need to have vectors in order to basically decide or in order to build the decision function, the classifier decision function, and then decide is it dog, cat, bot, or bird. So the fully connected layer is a fully connected basically because all the neurons in layer L plus 1 are connected to all neurons in layer L, which is different from neurons in the conv, which are neurons in the convolution layer. They are called locally connected because they are connected to local regions within the input image, not the whole image, for example. So the decision function always in the last hidden layers in your network, they are fully connected. Just also to consider that. That's why we need to convert the last layer of convolutional to fully connected by flattening, doing flatten and also concatenation of the feature maps. What the meaning of that? Let's assume we had 3 neurons. We applied the convolution and pooling of these 3 neurons, which resulted in 3 feature maps, new 3 feature maps. So now we need to move to the final decision. What we do first, we do flatten, which means we vectorize this matrix. So it will be 7, 7, 7, 7. We vectorize this one, it will be 1, 7, 0, 2, then 3, 5, 5, 4. Then we concatenate. So we just concatenate these vectors together to build one features vector, for example. Then we do fully connection. So this now would be like an input neurons to the next hidden layers, like the fully connected hidden layers, where the neuron here is connected to all the inputs. Neuron here is connected to all the input. Then we might have also some hidden layers here, not a problem. Then we have the softmax at the end, where we decide now is it a cat, dog, or whatever. So this is a fully connected. And this is now the general architecture of convolutional network. It has convolution followed by nonlinearity, which is or the activation function, which could be removed, tan x, sigmoid, whatever. And then we have pooling. Then we could have multiple convolution layers, for example, then convolution pooling, and so on. We could have a dropout in between for the regularization. For example, we could have dropout network here or layer, like we see in the regularization. We could have a batch normalization also in between to normalize the batch to increase the universality and also to increase the learning speed. And at the end, we need to do fully connected. And after fully connected, of course, we have the sigmoid, the softmax, at the end to do the decision. So what are the main configuration parameters or the hyperparameters of your network? Of course, one is now besides the number of neurons and number of layers which are coming from feed-forward neural networks, we have now 3 other filters, or actually, sorry, parameters. The first one is the kernel or template size of these features. Is it 3 by 3? Is it 5 by 5? Is it 7 by 7? You can see here basically we need always to have a feature size where we have an origin of the, for example, 4 by 4, we couldn't have origin. So we need to have 5 by 5 because we need to have the origin pixel or the center pixel like here, because this is where the result of the convolution will be stored in the feature map. So it's either 3 by 3, 5 by 5, 7 by 7, and also you can 11 by 11. So this is basically the kernel or template size. Now, if we have the kernel size decided, the second one would be the stride or step size. The idea of stride or step size, we said that in convolution we move along the image. The question here, do we move pixel by pixel? Like when it's pixel by pixel, it's stride equal to 1 or step size equal to 1, which means I would move now from here to the next position, which is the next pixel directly. And I would continue doing that until I finish from the whole image. That means, of course, if we are talking about stride size equal to 1 along x and y, or along rows and columns, that means also in the next row, when I finish from this row, I will also move 1 row only and do the convolution. And we would end up with this image here, which, as I said, is smaller than the input image because we started from there. So we already actually ignored some pixels there. Not ignored in the calculation, but ignored in the feature map. So they won't have value, or they won't have actually present in the feature map. And we started here and we ended here. So as you see, for example, we started there and we ended here. So the feature map size is 10 by 10. Which is not a problem at the end, as I said, because we actually need to reduce the size of images. So starting from 11 by 11, we ended up with 10 by 10. Now, if I have stride equal to 2, the image size will be smaller. As you see, for example, by stride equal to 2, that means I'm moving 2 steps at each convolution. And I would end up with basically 5 by 5, for example. From 11 to 11, we end up with 5 by 5. This would be actually our image, which here in the blue, and we can concatenate, of course, them to have one image. We downsample this. This is also another downsampling because we reduce the size. So the third one is, do we have a padding or no padding? As I said, in this case, we start from here, and we cannot start from the top, basically left corner there. The idea of padding is basically to be able to start from the top corner by adding zero padding. And zero padding is just an extension of the image with pixels that have value equal to zero. Like this one, for example, we extended the image by one column and actually two columns, which is before the first one and after the last one, and two rows, which is before the first one, after the last one. Then we can start from the first pixel of the image. Now here, this value, they are equal to zeros, so the multiplication of the convolution will be equal to zero, or the dot product with respect to this will be equal to zero. But we start from the first pixel. And if we do that, then with the stride equal to 1 and zero padding, we end up with the same feature map. So the feature map here equal to the image size. Now, this is usually important if we are looking for features that could actually be present at the border of the images, and so not only in the middle or in the basically in the scope of these images, so it could be on the border. And these are, as I said, hyperparameters that also usually need to search for the best combination of hyperparameters using cross-validation. And this is, for example, if we have now stride equal to zero padding, we end up with 6 by 6. So it's the size is reduced, of course, because of the padding, because of the stride, sorry, but it's bigger than without padding, which was 5 by 5. Now here we have basically a comparison between these five scenarios, where first one we have zero padding and one stride. And this would be our output, which basically we started with 5. And here we ended up with 5, as I said. We have what is called full padding, full zero padding with one stride, where we not only extend by 1, we extend by 2, in order to basically start from this position there. Then here the output image would be actually bigger than the input image. This, if we want to upsample, actually we can use that. We have no padding at all and two strides, of course, then the image will be reduced to 2 by 2. We have zero padding plus two strides will be reduced to 3 by 3. We have here zero padding, two strides, but also with a bigger image. So this basically the size is not matter here, but here we have more pixels, which also would end up with 3 by 3. Okay, because here we have basically 5 and here we have 6. So if we have 5 or 6, we end up with 3 by 3 feature map. So the common convolutional neural network architecture using this, they are basically now common neural network architecture that can be used in different scenarios, like in medical imaging, like in self-driving cars, object recognition, and so on. The first one, it's called VGG 16. It has also other, let's say, here numbers, or basically other versions. So the VGG, as you see, it starts with 64 neurons in the first convolutional layer, which means we have 64 filters in the first convolutional layers. The size of the first, or the feature map from the first neural network, or the first layer, will be 224 by 224 by 64, because we have now 64 feature. Then we have the second convolution, which is 112, 112, 128 feature. The third convolution, we would have basically 56, 56, and 256. The red one here is a max pooling, and the blue one is a convolution. So if we see basically 2, that means we have 2 convolutions here, 2 convolution layers that they have the size 112, 112, and 128. So we have here max pooling, then we have 3 convolution layers. Then we have max pooling, 3 convolution layers with different size. We can see now we started with 224, to 28 now, then convolution, and 3 14, but here we have 512 neurons at each of these convolutional layers. Then we have the last max pooling. Then here we do the flatten. So if you multiply 512 by 7 by 7, you would get actually that value here. And this is basically now the fully connected network, which would end up with thousands features for the final decision. Another one is called the ResNet. The ResNet is basically this similar architecture where we have convolutions. Here we don't have actually pooling at all. But the difference here that we have the residual network that we talked about before, which is used basically to avoid gradient vanishing. So we have this is skipping connections, it's called, where we skip here some connections and we basically use them to avoid the gradient vanishing and gradient explosion as well, and mainly gradient vanishing. So ResNet is now one of the most famous network. Is used in almost every real life application, like in self-driving cars, and also used in actually used in AlphaGo game because the board of the AlphaGo can be considered as an image with pixels. So this is where ResNet is used. So in general, there are different architectures as well. We have the LeNet, for example, which was proposed in 1998. We have AlexNet, we have ZFNet, we have GoogleNet, we have BigAG, we have ResNet. So I introduced to you the most, let's say, state-of-the-art architectures. Here we see the number of parameters. This 60,000 only, 60 million, 4 million, 138 millions. This is basically could vary, but you can see also that from basically 1998 until now, the number of neurons could basically increase, or actually is increased here kind of exponentially, because now we have more computational power comparing to 1998, and also more images, more data. And in general speaking, the deeper the network, the more neurons we have, the better the network is. So the bigger, the better. I'll just now present to you some simulations that are online, that just to understand also, or to more understand how you. So if you go at this URL here, which is, or you can Google Keras GS, and the first one you can select it. You see here basically different examples of convolutional network mainly. And we can start with the basic component, which is used for MNest. MNest is handwritten recognition, or handwritten, digits recognition. The idea, so for example, is our input space, input image, and here, for example, I can write number 3, and it would recognize number 3. So the first thing here to consider is that we have this basically 10 digits here from 0 to 9, and each digit here has a kind of a probability value. This basically represents the 10 output neurons with softmax. Okay, so the higher the confidence here, that means the softmax value here is the higher or highest. For example, I put 1, it's also very confident that is 1. If I put something like this, that's good. And if I put something like this, it's 2. For example, here 1 is a bit also started to be high. Now we have 6. Just trying to, now we can see also 0 and 1 and 2. Of course, there's not 2, but the network wasn't actually trained to recognize such a thing. But anyway, for example, now between 6 and 9, 6 also has a between, you see now 0, between 2 and 7. Anyway, so this is basically the output of the softmax. The other important thing to go see now, let's say 2 again, the output of the convolution. So here we see that we have 32 neurons, which means we have 32 filters. These are the 32 filters. And this is the result of the 32 convolutions that are done with these 32 filters. So they have basically valid padding, which means here we don't have zero padding. And we have here 33 by 3 filter. So each filter has a size of 3 by 3 with no strides, which means we have one step moving. And we can see now some kind of highlights. So in order to understand these highlights, it's better to move for the activation function and also for go deeper now, because here mainly what is happening here is edge detection, as I said. So we have like different edges are detected, which are highlighted in different feature map as we see here. So the next part is the ReLU, which would actually set all the negative values to 0 and keep the positive values. Now, if we move to the next convolutional layer, which is convolution activation, we start to see now features. Because here we start to see now some kind of really highlights where certain features are detected. Okay, for example, here we have these two features are detected and they are learned by the network automatically. They are learned by the network that they, for example, the three, they could highly be correlated with the digit 2. We usually see redundancies in network. For example, you can see that this neuron and this neuron, they are doing almost the same. And this, if we apply some kind of regularization like dropout, for example, or you apply L1 regularization on the activity or on the activation, then we might reduce its redundancy within the network. The next part here is a max pooling. So now we are just downsampling, which means reducing the size of these features by using max pooling 2 by 2 with one stride. Then we have dropout with 0.25. So dropout, as I said, it will drop out some neurons with 25, which means 25% of the neuron would be dropout at each training iteration. Then flatten, which would now convert these feature maps into one vector. As I said, it would be first doing the flatten, then concatenation. So here we see now 1D vector that has all the features inside. So basically, here there could be some features that are not on now because they were not observed by the input. And whenever we see here dark, that means these features are detected. The next part would be here the dense. So now we have another fully connected neuron or layer. So this is basically every neuron here would be connected to all the neurons in the layer before, which has activation. Now we see we are reducing the size, we are reducing the number of features. We also have a dropout there to increase universality. And finally, we get the dense here, which has a size of 10, which we apply softmax at the end. And we see now softmax here is basically telling me, yes, this is the feature, which is number 2. So softmax here has a size of 10. 0 means digit 0, and 9 here is the digit number 9. So if we apply different things, for example, what is different from, let's say 4 has some kind of unique features. Example, this feature, you can see it now here detected, that is important for number 4, and the indices of softmax is a number 4. So this is how ConvNet mainly work. We can see here variational autoencoder, or actually the autoencoder. Now we talked about autoencoder and we talked about the latent space, where it is the middle layer where we have representation. This here represents a representation of the digits, again, the handwritten digits, which actually two neurons here. So we have two features only in the activation, and they have the value between -1 to 1 and between -1 to 1. And when I change the value here, so this basically I'm just changing my value within that space, latent space. we can see the output, the reconstructed output, which is the output of the decoder, would have different image. So whenever I move that, this will see the meaning of representation in the latent space. If you don't understand that, please ask me anytime and I will explain more details. So we have seen ResNet, which is it's much bigger as we see now. That's why it takes longer to upload here. This is trained on ImageNet dataset, which is a general purpose image recognition or object recognition dataset. So we can here select any image you want, or actually you can select from one the set here. For example, we have a bird image. And we start here to see now the ResNet. So the ResNet has input layer, of course. The images, they have the size 224 by 224 and 3 colors, so red, green, blue. In convolution network, when we have 3 channels, we do the convolution at each channel separately, then we concatenate the features together, like what we do with the convolution layer with different filters. So what we have done here, basically, when you have this input, we have the convolutions, and we get that 100% is the hummingbird. Now these are the other, for example, possible classes. Just looking at the architecture, as I said, ResNet is very deep network. It starts with input layer, then we have convolution, then we have batch normalization, then we have activation, then we have max pooling, then convolution, then batch normalization, and so on. We have here the ResNet, the residual, where we have here basically skip connection, as you see. And here, for example, we have another block, and we have another skip connection, another skip connection, and so on. Sometimes they add also another convolution within the skip connection. This just human are basically designed network. So they try different architectures, and they end up with this as the best architecture to basically perform the best. So these are very deep network, as you see. We have here 100 possible outputs. So it's basically, if we look here we have just a small set of the 100 possible object, or actually object that this network can recognize. For example, violin, here we take an image of the whale, for example. It's still now processing. What we can see here, okay, it's not possible, but with the inception, possibly it could be possible. Inception is the Google network, which is again it's convolution network, but has a different architecture. ResNet performs better than Inception. This 50 means there are 50 layers there. So it takes a while. Okay, so here we take, for example, the fox. So we see the Google Net is basically first start again convolution, batch normalization, activation. There is no pooling, or here we have the pooling. Then there are also some kind of parallel here, convolutions and pooling, and there is concatenate there. So the difference between the skip connection and here ResNet, sorry, the inception here. In ResNet we have here add, so it's basically they should have the same size. This, for example, this path and the result of this path should be the same size, and then we add them together, element-wise adding. But in this case, we have basically concatenation, so just basically concatenate the result together. So it says here it's red fox, and if I hover over, basically, if I look here, is telling me what are the strong features that are considered here to decide that this fox, or what are the strongest features. And here is telling me the eye. So the eye is the strongest feature by the activation maps, the feature activation maps. If I put here bird, if your browser support GPU and you have a GPU on your mobile, on your laptop, sorry, then the processing would be much faster. So the prediction would be much faster. So now it's telling the bird, and again, it's basically this region is what is considered, of course, to decide if it's a bird or not. So this is about convolutional network. Uh, in the papers review that you will have to do, some papers are related to convolutional network, which makes you understand them deeper. They are widely used for image recognition, as I said. The main building blocks of them, you just learned about them, which are the convolution and pooling, and of course the others which can also use for other architectures like the patch normalization and dropout and the residual connection. If you understand the functionality of these blocks, then you would understand any architecture or any proposed architecture for convolutional neural network. Thank you.